Um, I will pass back the quiz from last time at the end of class. I put the um solutions to that one on Google Drive. Um, Also, yeah, we got the new problem set today. That'll go from this Wednesday to next Wednesday. And then I think I think there might be well, I'll talk about the next exam. I think what I'm gonna do is send out a poll because it's currently scheduled for July, at least on the syllabus it said July 15th. I was gonna set out a poll so that y'all can decide if we want to have it on that day or if we want to do the same thing as last time and push it forward so that it's on a Monday instead of on a Wednesday, which would give you the extra like Thursday, Friday, Saturday, Sunday to prepare for it. If we do it that way, instead of that Wednesday being the test day, that Wednesday I would end up having to cover the stuff that you would see on the like that would not correspond to the exam just to have something to do on that day. But so I'll send out a poll for that. It's totally up to y'all how y'all want to do that one. Um, and yeah, today we're also getting the reactor design problem. So that's like the first thing that I was going to start with. And that's kind of continuing on from last time. Last time we talked about how if you have like a heterogeneous system, meaning just like a system that contains multiple pieces of different materials, there's a approach that we can go through to homogenize the cross sections for those different materials so that we can do calculations in a more simplified way. So this is an example of like a unit cell. This would be like one fuel element inside of a larger nuclear reactor core. And I should probably label that the blue part would be like the coolant or the moderator. And in our equations that we use to homogenize cross sections, we use the volume fractions of each region. So like this entire thing is my unit cell. And we're going to want the volume of this entire unit cell, and we're also going to want the volumes of the individual regions so that we can make volume fractions, which would be like the volume of the particular region divided by the volume of the entire cell. So we're going to define the radius of the fuel, which is the pink is the fuel, the gray is the cladding. So the radius of the fuel just goes from the center of the fuel element or the center of the fuel pellet to the outer radius of the fuel pellet. And then we're going to define the clad radius to be the distance from the center of the fuel element to the outside of the fuel element. So the distance from the center to the outer edge. If this is the radius of the clad and this is the radius of the fuel, then what would be the little thickness? If I call that little thickness just a dx, what would that thickness be based on the fuel and the clad radius? Perfect, right? It's clad minus fuel. And that would be helpful to know if you wanted to perform a volume, if you want to find the volume of that clad. It's not just the full circle, but it's the difference between this big circle and then this smaller circle inside it. There's also we're also going to need the width of this fuel, sorry, the width of this unit cell. So like if I were to measure this distance right here, that's the width of the unit cell. And if we have a bunch of fuel elements inside, like if we're looking at a lot of fuel elements, this distance, the width of the unit cell, we give it a name and we call it the pitch. So pitch, we use the symbol like a capital P for pitch, and it's a distance. It also would have units of like centimeters. And the pitch would also happen to be if you had a bunch of fuel elements, it would also be the distance from the center of one element to the center of another. It just depends on how you kind of set up your unit cell. Um, but so this would be cell centered. This structure, this unit cell is cell centered, and so the pitch also represents just the width of that unit cell. So that was what that is. And if we have that, then we can compute fractions. We can compute the volumes of the individual parts, and we compute the volume fractions from the individual volumes. We're imagining that we're looking at this like on like from a bird's eye view, and so in reality, the reactor core is going to have some sort of height. So like if we were to think about that height into the page, that height h. Um, is also going to be some distance in centimeters. If you're so yeah, that height is there as well. And we would need that height to actually compute volumes instead of just areas. So like if my unit cell is a square with a width of p and then it goes a depth h into the page, what would be the volume of the full cell? Perfect. Yeah, it's going to be like the area of that square, which would be p squared, and then we also multiply by h to turn it into a volume. Um, Perfect. How about so the fuel here, the fuel is like a cylinder. Like we're seeing the circle, but it goes down into the page, so it's really a cylinder. So what would be the formula for the volume of the fuel? Perfect. And the r pi r squared, and that r would be the for the radius of the fuel times h. Perfect. So notice, if we have the volume of the cell and the volume of the fuel, we could do volume of fuel divided by the volume of the cell to get that volume fraction. And in that case, if we needed the volume fraction, the heights would just cancel out. But if we wanted to know the individual volumes, the height would be important. Um, how about the volume of the clad? What's the volume of the clad going to look like? Perfect. Yeah, and so it's going to be like the area of this big circle minus the area of that little circle, basically. So I'm going to have a pi on both terms, and then I'm going to end up doing r clad squared minus r fuel squared. So that would be like the area of that little circular shell or like that little circular wedge. And then if I multiply by the height, that would give me that volume. And if we know the full volume of the cell, and then we know the volume of the fuel, and we know the volume of the clad, how can I get the volume of the moderator, which is basically just like everything that's left over of the other two parts, right? Yeah, perfect. So she's saying we're going to take the volume of the cell, which is the entire volume, and then we're just going to subtract off the volumes that aren't the moderator. So we're going to subtract off the volume of the clad, and we're going to subtract off the volume of the fuel. Awesome. So that would be how I would compute the geometry can sometimes be hard, but that's how we would compute those individual volumes. And then with all of these individual volumes, we could do V mod over V cell to get the moderator volume fraction. We could do V clad over V cell to get the clad volume fraction, and we could do V fuel over V cell to get the fuel volume fraction. And yeah, so awesome. That is something that you're going to have to do on the reactor design problem. So I just wanted to make sure we were comfortable with those geometry parts. And at this point, we basically have seen everything that we need to be able to do the reactor design problem. That reactor design problem is going to be due on the last day of class, which is August 3rd. There's a submission for it on Canvas. So like if you go onto Canvas and you look under Canvas is kind of weird in that I haven't really been using it for the class. So you might not have been on here that many times, like for this class. So I just wanted to go. Oh, that is not. Oh, I think I can go here and then here. Um, so you'll submit the reactor design problem on Canvas. If you go into our class, and then I want to view it as a student. What you want to do is just go into modules. And then it's basically the only thing that's here. This is the only thing that you're going to end up submitting on Canvas. So that's why I haven't really cared that much about Canvas. And if you go here, that's where you could like start the assignment to submit your deliverables. So yeah, that's where you would go to actually submit it. It's due August 3rd at midnight. So make sure that, and so August 3rd is our last day of class. On that last day of class, we'll do like a little bit, we'll do a combination of final exam review and also like last minute Q&A for anything that we might be wondering about. And I assume that we'll be talking about the reactor design problem more, like when we have our help sessions. Those would be good times to ask about the reactor design problem. But yeah, just wanted to make sure that we knew where we would end up submitting it when we submit it. And that is a firm deadline. If you turn it in after that, then you're going to get a penalty per day. That is a increasing penalty. So it'd be 10% on the first day, 20% on the second day, 30% on the third day, 40% on the fourth day. We have until August 3rd to do it. So like if we start soon, it's very doable. I would not wait until the last minute because it's not that you couldn't do it in like a weekend if you had to, but it's that if you start the weekend before it's due, you're going to end up with some questions. Like you're going to get stuck on a certain part probably. And depending on, from person to person, where we get stuck might be different. But you want to start early enough that you give yourself time to ask questions if you end up having questions about doing it. Question. Sorry, can you repeat the question? Yeah, yeah, absolutely. If you have questions about any of your results, I'd be happy to go over any of that with you. I was also planning on posting some information that would be helpful in terms of like one of the things that you're going to end up getting is cell average cross sections for all of your different regions. And so you're taking all of your regions and then homogenizing them to get cell average cross sections. And what I will do is I'll say, if you plug in this enrichment, these are what your cross sections should look like, which is a good way to verify that that part of your code up till that point is correct. Because if you get the cross sections right, that's probably one of the harder parts is just getting all of those numbers to work out the way that you want them to. So I'll post some stuff that'll help you verify your answers. But then, yeah, if you want to come and ask questions at office hours, I'd be happy to like look it over and say like that number looks a little off or something like that. Hmm. Yeah. No, it's just one. And I mean, I think on Canvas you can like resubmit if you need to. So yeah. So the design, oh yeah, and just make sure that we're aware that the reactor design problem is 10 to 20% of your grade, and that's like it's a range because when I'm doing grades at the end, I pick that range such that it helps your grade the most. So like maybe we don't do so well on the quizzes and we don't do so well on the first exam. So those would end up having the lower weights. And if that's the case, like if we're struggling on the quizzes and if we struggled on that first exam, those will end up being on the low weights, but that means that everything else needs to be improved because those are the ones that are going to get the high weights. So the reactor design problem is a good way to secure like a good 20% or so of your grade. And that's effectively the same weight as all of the quizzes. So that can definitely help balance out if you were struggling with those quizzes. Um, the reactor that we're considering is a sodium cooled fast microreactor. Fast reactors are really cool. They are becoming more relevant. They have a lot of operational experience. In Russia, they've built a bunch of them. And part of the reason that fast reactors are cool is because, like, as nuclear engineers, when you talk to people and you're like, I study nuclear engineering, one of the things that they will ask you is like, what are we going to do with the waste? The waste is this big problem. And the fast reactors are like the easiest answer to that question in terms of like you don't have to keep the waste in like spent fuel canisters for millions of years. At some point, we're probably going to want to use that waste because we can take that waste, put it in fast reactors, and with a fast neutron spectrum, you can actually fission a lot of the actinides that are built up in your spent fuel, and so you can actually get energy out of the waste by putting them in a fast reactor. So that's one reason that fast reactors are cool. Fast reactors don't use a moderator, which allows you to make more compact, smaller reactor cores. And that can help reduce some of your design complexity and maybe some of your cost, depending on like other trade-offs, obviously. But that's one way that those reactors are like kind of more simplified. And you can also design fast reactors in such a way that they make more fissile fuel than they consume. And those are what we refer to as fast breeder reactors. So at, at some point, like we have a finite amount of uranium on the Earth, especially like uranium 235 is the more, is the harder thing to come by. And fast reactors are a way that we could continue to make power from fission by either making fissioning the waste or making fast breeder reactors so that we can take like the uranium 238 and have it produce new fuel. You can also do the same thing with thorium. You could put thorium in a fast reactor and make thorium will absorb a neutron, and then eventually it becomes uranium 233, which can fission at any energy. Also, if it's in a fast reactor, thorium itself can just fission on its own. So fast reactors are cool. Um, because of the fuel packing in a fast reactor, they have these hexagonal assemblies, which look kind of different from the square assemblies that you see in like light water reactors. So the fuel elements have a triangular lattice instead of a square lattice, and that means that your unit cells end up also being hexagonally shaped. So this is like what your unit cell is going to look like in your sodium-cooled fast reactor, where the light blue is the fuel, the dark blue is the clad, and then the other different light blue would be the coolant. So the pitch is like this side to side distance, and then you have your fuel radius and your clad radius, and that stuff is given to you in the problem. So this is like our unit cell. We've got this unit cell made of different materials. We're going to go through a homogenization process where we collapse all those cross sections together so that we have like a single type of. So we'll have a cross section for our entire cell, and then we can do all of our multi-group, multi-group zero-dimensional diffusion calculations based on the cross sections for that cell. That'll allow us to get the flux group components, which will allow us to get the K effective, and then we will go through a process where we update the enrichment of our fuel until we get the K effective that we want. Um, so this is what I was talking about in terms of homogenizing the cross sections. You've got three different materials here, which will be the fuel, the clad, and the coolant. And the way that you can get a cell average cross section for this reactor is you take those individual cross sections and then you multiply them by the volume fractions of each material. So that was why I was talking about why we would need those volumes, is because those volume fractions are going to be involved in the cell homogenization process. And this is the formula that you'll need to use for the volume of the unit cell. If you know the pitch and you know the height of the reactor, then this is how you can get the volume of the cell, and both of those things are given to you. Um, Last time, we said that this definition can be inaccurate if you have a reactor that has to be treated as heterogeneous. And that's because we're missing the flux disadvantage factors, which were telling us about the ratio of the flux in a region to the flux over the cell. Does anybody remember why we can neglect the flux disadvantage factors if it's a fast reactor, which can be treated as homogeneous versus heterogeneous? So the question was, why can we neglect the flux disadvantage factors for a fast reactor versus like a thermal reactor? It has to do with the moderator for sure, and it has to do with the fact that if you have a moderator, then it's going to slow your neutrons down a lot, which is going to change your flux profile. So if you were to compare the flux in the fuel to the flux in the moderator, in a thermal reactor, those are going to be very different. Whereas in a fast reactor, the flux doesn't change that much from region to region. So all of those flux disadvantage factors, which is like the flux in one region divided by the flux of the cell, those are all going to be approximately one. And that means that technically they kind of drop out of our equation. So this homogenization process really only works if you have like a fast reactor, or in other words, if you have a reactor where the flux doesn't vary very much from region to region. So here we're going to say that in fast reactors, there is little variation in the flux from region to region, from region to region. So yeah, if you try to do this for a thermal reactor, your results are going to be really bad. That's partly why we picked this reactor for this problem, is because it simplifies our calculations and will also make our still give us relatively accurate, reasonably accurate results. So in our reactor design problem document, you have a table of some values. These are like the design parameters of the reactor. Um, One of the things that we need to know about is the kind of fuel. And in this case, we're going to assume that it's uranium metal that consists of just uranium 235 and uranium 238 kind of like mixed together. So you're given the density of the fuel. And then here we're saying that the fuel combination is some enrichment percentage of the uranium 235, and then the rest of that fuel is uranium 238. Like if this X was 5%, then this 1 minus X would be 95%. So if I know the cross section for my uranium 235 and I know the cross section for my uranium 238, those are gonna combine. Those cross sections would be additive to give me an overall cross section for my fuel. And if I want to get if I wanted to get the microscopic cross section for uranium 235, sorry, macroscopic cross section for uranium 235, what two things do I need to multiply together to get a macroscopic cross section? Microscopic? Yeah, microscopic cross section for 235. And then I need to multiply that by something. Yeah, N. And that's the number density of 235. So like for any reaction X, that would be how I would get the cross section for uranium 235. It would look just like that for uranium 238, except it would be the values for U238. So this cross section for any reaction X and for any group G for the fuel is going to look like the micro cross section for that reaction for that group for 235 times the number density of 235 plus the micro cross section for that reaction for that group for 238 times the number density of 238. So microscopic cross section times the number density gives us the macro cross section. And what's my formula for the number density? How do I calculate number density or atom density? Rho times something divided by something. The big mass goes in the bottom, so the atomic, yeah, and then avocado number goes in the top. And so that's like the general way that you can write it. But here, because we have this mixture of nuclides, we have to also include, yeah, you have to also include the enrichment percentage. So for like your for 238, it's going to be 1 minus that enrichment times the density of the fuel times Avogadro's number divided by the atomic mass of 238, which would be 238 grams per mole. And then for 235, it's going to look very similar, except we're going to have the X, which would be just the 235 enrichment. We still have the density of the fuel. We still have Avogadro's number. And then the atomic mass for 235 would be 235 grams per mole. So if you plug in the density of the fuel in grams per centimeter cubed, and then you plug in Avogadro's number, which is Ava, what is it? 23rd? I think it's 23rd. And then what are the units of Avogadro's number? A yeah, atoms or particles per mole. Atoms per mole. So if you put Avogadro's number here, then the moles cancel out, and you just have number of particles. And if you plug in the density of the fuel in grams per centimeter cubed, then the grams cancel out, and you have overall a number that has units of atoms per centimeter cubed. So that's why it's an atom density, number of atoms per unit volume. So those are the calculations you would use to get your number densities. And when you start, you're just going to pick an enrichment for uranium-235. Like maybe you just start by assuming it's 5%. And then you're going to go through all of the calculations in the problem. You're going to end up getting your K effective for that configuration. And you're going to look at K effective. And if your K effective ends up being too low at a given enrichment, what do you have to do to the enrichment? Increase or decrease? Increase, right? So I would just pick a number like 5%, calculate my K effective, and then increase that K effect, increase the enrichment until you get to the K effective that you want. And then also in here, we have information about the coolant. So the coolant is sodium, and you're going to be given microscopic cross sections for sodium, which means that you're going to need to also compute the macroscopic cross sections for sodium, which means you're going to need the number density for sodium, which means you're going to need the density for sodium. So for the density for sodium, you're going to need to look that up. That's going to be a lookup. The only thing you want to kind of be aware of with that is that sodium, the density varies quite a bit with temperature. And these fast reactors are going to have a temperature of around like 500 Celsius to like 600 Celsius. So when you're looking up the, oops. So in that case, it's going to be when you're looking up the sodium, just make sure that you're getting the density for like a temperature range that's reasonable for a fast reactor. Um, the cladding, the cladding in general would be made of like stainless steel, but we're gonna simplify the steel as just being iron. And so you're also going to need to look up a density of iron. Um, yeah, iron density isn't going to change as much. But yeah, you would want to get it for like a reasonable, at least for yeah, try to get it for a temperature that's relatively close to that. And so with the core height and the core diameter, that's how you can get the volume of the core. And then we've got all of this other information right here. So I guess technically this extrapolation distance is also gonna go into the volume of the core because we have to add extrapolation distances to those geometry parameters so that the equations that we use for like the BG squared for a cylinder make sense. So when you get with these pieces of information, you can get the volume of the core. You can also get BG squared for a cylinder. You just have to make sure that you correct for these distances when you compute the BG squared. So these corrections, technically these corrections, I don't want to show that arrow. That is going to be involved when you calculate BG squared because BG squared is based on the extrapolated dimensions. And in the problem statement, I give you a little hint about how you would calculate that BG squared in terms of how you add this correction factor to the height and to the diameter. And then this information right here, that's used for your volume of your cell and the volumes of your regions. And then I give you a power as well. So yeah, that just hopefully helps us get a better understanding of the information that we have, kind of what parts of the problem it's going to be used for. Um, these are the assumptions that we're going to make. So you're going to use the multi-group zero-dimensional model for the reactor. We're going to assume no reflector. We're going to replace that stainless steel with iron. And we're going to assume that all of the cross sections that I gave you are given at the operating conditions of the reactor and that they've been properly averaged over the range of the nucleus motion and also the range of the over the neutron energies for each group. So you want to use that information to get a core that has a K effective of 0.05 plus or minus 0.01. So that means your K effective can be anything from like 0.04 to 0.06. Um, in that document, which contains the precise details, I spell out like all of the deliverables for the project. So just make sure that you're following that pretty carefully and that you're including all of those pieces. Because whenever I'm grading your assignments, I'm just mostly going to be looking for, are you completing those deliverables? Um, And so, in general, this is kind of like what I was saying before, is that the enrichment is going to affect your fuel cross sections, which is going to affect your group flux components, which is going to impact K effective. So you just pick an initial guess for the enrichment. You do all of your calculations in terms of like converting your micro cross sections to macro cross sections. You get your cell homogenized cross sections, and then you use the zero-dimensional multi-group diffusion equation to get your group flux components, which will give you K effective. And then you just increase or decrease K effective, sorry, increase or decrease the enrichment until your K effective is in the range that you want. And so that's where the iterations are involved because you're going to have to repeatedly change X to get your K effective. And if you do it by hand, it's just going to be a mess. So, what do we have to show every version of X and change it just a line? You will probably, whenever you submit it, I would probably want just the final version. But one of the things that you're actually going to have to give me is a plot of K effective as a function of the enrichment. So that's like another place where you're going to have to vary the enrichment to get K effective. Like, so in my Excel sheet, my final version has the X that corresponds to the desired configuration. And then I just like kind of manually changed X and then I copied from that cell, copied it just as a number to get a column of these are my X values and these are those K effective values. Um, so yeah. Um, Excel, I think, is a good way to do it because it's very easy to see all the multiplications that you're doing. Sometimes because you have these big matrices of, well, these big cross sections end up going into a matrix. And so if you are doing it in like a code, if you're more comfortable with coding, it's not too bad, but it can be easier to just see everything in Excel. I did in Excel. I have no problem if you do it in Excel. Just do it with whatever tool you're more comfortable with. So yeah, that's everything I wanted to just say to like get you introduced to the problem. That should give us a pretty good starting point. And then I would hope that over the next remaining weeks of the class that we're making progress on that and asking questions as they arise. Please don't wait till the last minute because if you wait till the last minute, I'll still try my best to help you, but it just becomes harder to help if we wait too long. Yes. Yeah, yeah. None of the new stuff that we cover from here is going to go into the reactor design problem. So you can do the reactor design problem based on the last like 3 or 4 lectures. Yeah. So yeah, at this point, we're going to get into time dependence in more detail. This is the topic of chapter 6 in the Svegtov notes. At this point, we've mostly been considering steady state problems in that we've been looking at critical reactors in different kinds of detail. And so in chapter 6, we're going to study time dependence more to get a better understanding of how things like the neutron population and other factors of our reactor, like the power and the power density, would evolve with time. So, like, if we imagine a reactor is critical and in steady state, something that might happen while that reactor is operating is an operator might remove a control rod from the reactor core. That change in the system by removing that control rod is going to change stuff about our system. Like if the reactor was critical and then we remove a control rod, what's going to happen to the absorption rate? It's going to go down, right? The absorption rate is going to decrease because now we have less absorbing materials in our reactor. Those materials were previously helping our chain reaction be balanced, and now there's a lot less absorption. So how does that mean if before we were critical, which means production and losses were balanced, what's the production rate? How's the production rate going to compare to the loss rate once we pull that control rod out? Yeah, perfect. The production rate is now going to be greater than the loss rate. We're now producing more neutrons than we are losing from the system. And if our productions are bigger than our losses, we're now supercritical. Perfect. We're now in a supercritical configuration. You have to be supercritical at some point. Like when you're starting the reactor up, you end up having to kind of slightly go supercritical and then let things balance out. And things will balance out for reasons that we'll talk about later. There's feedback effects, usually relating to temperature. But yeah, so supercritical isn't always bad, but if you're supercritical and you're not intending to be, then that's where you could have problems. And so this kind of helps us just to kind of conceptualize that changing various aspects of our system can affect what our system does. And as a function of time, we want to be aware of those things because that's going to be very important to like the safety of our reactor and accident analysis and things like that. Um, so one of the things that we need to kind of revisit is the fission process. This was the fission process that we had introduced like very early in the class. We know that like a neutron comes in, hits a fissile nucleus like maybe U-235. That U-235 nucleus begins to split in two. And once that nucleus splits, we get these two fission fragments. And those fission fragments will also immediately start releasing some neutrons. So the neutrons that come right after the fission event, we call those prompt neutrons. These are the neutrons that are emitted promptly after the fission event. And notice that this was one fission reaction, and we get multiple neutrons out of that fission reaction. And I mentioned that because when I was looking at our exams, it looks like some of us are mixing up the fission rate density with the production rate density. And so like the fission rate density is like a sigma F times the flux. So that tells you how many the number of fissions per unit volume and per unit time. This was one fission event. So this one fission event is not the point that I'm trying to make is that these two are not the same. They're related, but they're not the same. And the reason that they're different is because the production rate density has a multiplier up front, nu sub f. And that nu sub f is kind of like this. It's telling me about how many nu sub f is the number of neutrons per fission. So notice here, nu sub f was like 3. And for 235 uranium, it's like 2.4 to 2.5. So if anybody says what's new, you could be like about 2.4. And so just keep that in mind, right? The number of fissions per unit volume per unit time is not the same thing as the production rate. This is what tells me about the number of neutrons released from fission per unit volume per unit time, but they're not the same. Every fission event produces multiple neutrons. And so these, though, are just the neutrons that come right out of fission. What happens later is that these fission fragments themselves are still highly radioactive. And we produce all kinds of different fission fragments in our nuclear reactors. And some of those fission fragments are really interesting because as they decay, they will actually emit multiple, maybe some of these fission fragments will emit more neutrons as they continue to decay. And so we get more neutrons than just the prompt neutrons because some of these fission fragments will beta decay. So due to the beta decay of our fission products. And there's also technically a difference between the fission fragments and the fission products. The fission fragments are what come immediately out of fission. And then as those fission fragments decay into other things, those are what we call fission products. Those fission products, some of them will decay, and in that process, they will emit other neutrons. So the ones that get emitted later, that would be these guys. These neutrons that are getting emitted later, we call those delayed neutrons. And delayed neutrons are really important. When we talk about reactors and reactors being critical, they are critical on both prompt and delayed neutrons. So we have to account for them, and they are born at different time scales. Like the prompt neutrons have that name because they come almost immediately out of fission, whereas these delayed neutrons are born at at different like time scales, depending on the decay constants of the precursors that are producing them. So that's kind of like what are delayed neutrons. And then this is just explaining some of the physics of delayed neutrons and like how they come about. So bromine 87 is an example of a fission product that produces delayed neutrons. So like you might have a fission event that produces arsenic 80. Oh, question? Yeah, the prompt is greater than the delayed. Like usually the prompt number of prompt neutrons would be about 2 to 3, and then the yeah 2 to 3, and then the delayed neutrons you pretty much only get one each time. Yeah, good question. So this is like an example of a decay chain that might produce bromine 87. And bromine 87 is also a beta decayer, but he's a really interesting one because 2.6% of the time, instead of it just beta decaying and becoming krypton 87, it will beta decay into a metastable form of its of krypton 87. So this is what happens about 2.6% of the time, and this is what happens the other 97.4% of the time. And about 2.6% of the time, it becomes Krypton 87 metastable. And this really excited version of Krypton 87 wants to become stable. And the way that he does it is he kicks a neutron out of his nucleus. So this is where you get a delayed neutron. And then that Krypton 87 has now lost a neutron, and then it becomes Krypton 86. And that's that neutron that comes out. Um, So the nuclides that do this are special nuclides, and we give them a name. We call them delayed neutron precursors. Delayed neutron precursors. So there's lots of different delayed neutron precursors. We know about like over 200 of them. Um, they can either come immediately as like some of the fission fragments that come out of fission are delayed neutron precursors. Some of them are in the decay chains of those fission fragments. Um, we don't have to keep track of all 270 of them, thankfully, because only about a dozen of them or so are like practical in terms of the time scales over which they affect our reactors. So yeah, so delayed neutrons come from delayed neutron precursors. And so the way that we had been talking about our balance of our neutron flux or our neutron gains and loss rates, and like the most detailed context was the energy dependent diffusion equation. So this is just rewriting that energy dependent diffusion equation. And this this explanation is somewhat incomplete in that we don't have delayed neutron source terms in our none of this tells us about delayed neutron production. So what we need to add is a delayed neutron source term. So that's what we're going to do. We're going to add a delayed neutron source term. So all we're going to do is along with our fission. So this was our fission production term. And now we're kind of recasting that fission production term such that we're kind of separating out what is the prompt neutrons from the delayed neutrons. So this term that we were kind of treating as just like as kind of like a prompt term, we're kind of explicitly saying that this is the fission spectrum of prompt neutrons that are emitted from our fuel, and this is the number of prompt neutrons emitted per fission. And and we're adding on a delayed neutron source term. That might depend on energy and it might depend on time. So before, this new F was the total number of neutrons per fission, and it was kind of combining the prompt and the delayed neutrons, and now we're just splitting them up. That's the only change that I've made going from here to here. And so we've got this delayed neutron source term, and our question is, what does that delayed neutron source term look like? This is just spelling out all of our terms. We have kind of seen all of these before. The only ones with this equation, it might look complicated, but it's just a balance equation. It's just basically saying the rate of change, and the way that it's written right here is it's saying that the rate of change of my neutron population equals all of my losses. Sorry, it's the rate of change plus all of my loss terms equals all of my gain terms. So I have losses due to net leakage. I have losses due to the total interaction rate density. I might have a source term, like an external source term, like from californium-252 or some other nuclide that does spontaneous fission in my reactor. I have an in-scattering rate density term. I now have a prompt fission production term, and I have a delayed fission production term. And all of these are energy-dependent rate densities, so every term in this equation has units of neutrons per unit volume, per unit time, and per unit energy. So ultimately, we are trying to figure out what's this delayed neutron source term look like. So if we want to figure this out, we need to define some terms that are going to be relevant for our delayed neutron production. These delayed neutrons are coming from our delayed neutron precursors. So one of the things that we need are the density of those delayed neutron precursors, and that's what C sub I is. C sub I is the expected density of our type I precursors at some time t. It's a density, so it has units of inverse volume. And the I is because we have multiple groups of delayed neutrons that we need to keep track of. So this is for some group, some type I precursor. And those precursors are born into our reactor from fission events, and then they decay through radioactive decay processes. So we need to find the decay constant for those type I precursors, and that's the lambda I. That's the decay constant of our type I precursors. It's a decay constant. It's telling you kind of like about the probability per unit time of decay happening. So it has units of inverse seconds. And then ultimately, these are coming out as a result of, or really, neutrons are coming out of delayed neutron precursors. So we need a fission spectrum for the neutrons that come out of each type I delayed neutron precursor, and that's the chi sub I. That's the energy spectrum of the neutrons that come out after the decay of a type I delayed neutron precursor. It has the same units as the regular fission spectrum and kind of means a similar thing. It's just associated with neutrons coming out of those delayed neutron precursors versus the neutrons coming directly out of fission. And with these quantities, it kind of follows that if I want to get a source rate density, which has units of inverse volume, inverse time, and inverse energy, I could actually get it by just multiplying all of these quantities together. And then if I have multiple delayed neutron precursors, I would need to add all of those quantities up for each delayed neutron precursor type. So therefore, I'm going to have a big summation going from little I equals 1 to big I, and it's going to be the product of all of these quantities. So it's going to be chi sub I of E times lambda I times Ci of T. And this is going to be for I equals 1, 2, 3, dot, 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 all the way up to I, where I is the number of delayed neutron precursor groups. So I'll say the number of D and P groups. Typically, like 6 or 7 groups is the number that we use. So depending on how detailed you want to be, you might use more or less groups. But yeah, that's what big I is. So this is what our source term might look like. But to know what this source term is, we need to know what our precursor densities are. So we need some way to find what those precursor densities look like. And if we want to figure out what those precursor densities are, we have an approach that's our tried and true approach, which is to do conservation. So when we talk about conservation, we're saying some statement of change rate equals gain rates minus loss rates. And in this case, this is a balance of our type I delayed neutron precursors. So that's the population that we're trying to keep track of. It's our type I. I'm just going to say DNPs, and I'll say in the volume V. DNP is delayed neutron precursor, kind of shorthand, so that we can save ourselves a little bit of writing. So these delayed neutron precursors is the thing that we're keeping track of. And then we need to ask ourselves, how are these things born and how are these things lost? We know that the loss rate is because they are decaying. And so the decay rate density, the number of decays per unit volume per unit time, is just going to be the product of the decay constant and the concentration. So this is going to be lambda I times Ci of t. Can write that as a better lambda because it kind of looks like something else. So that right there, the decay constant has units of inverse time. The density, the precursor concentration has units of density. So those combined gives me the decay rate density. So, and that's the only way that they're lost is when they decay. And then the gain rate, we need to think about how they come about in the first place. And ultimately, they come about from fission. So the production rate is going to be kind of something that looks like a fission production term. It's going to be tied to the fission rate density. So the gain rates is going to look like the fission rate density. And we need to assume something about how many neutrons each delayed neutron precursor produces. And we're going to assume that it produces exactly one delayed neutron. So each delayed neutron precursor produces exactly one delayed neutron. So we are going to define something called nu sub di, and this is the expected number of type I precursors that are produced from fission. Produced from fission that is caused by a neutron with energy E. So this isn't telling me about the number of neutrons that come out. It's telling me about the number of delayed neutron precursors of type I that come out every time a fission happens from a neutron at energy E. And because every time we get a delayed neutron precursor, it produces exactly one neutron, one delayed neutron, this kind of represents the exact same thing as the number of neutrons, number of delayed neutrons emitted from type I precursors per fission caused by a neutron of energy. So in that context, it kind of means what we were probably thinking it meant. It's based on the number, it's telling us about the number of neutrons that come out from our delayed neutron precursors every time a fission happens caused by a neutron with energy. So we know that our gain rates are going to look like a fission production rate with this as my new term. And then the loss rates is this decay rate density. And then the change rate is going to look like rate of change of that quantity. So this is the change rate. And it's going to be equal to the gain rate minus the loss rate. And in this case, the gain rate is going to be the integral from 0 to infinity with respect to dE prime of that new dI, which depends on the energy of the neutrons that are causing that fission. And sorry, this should be a function of R and E prime, times sigma F as a function of R and E prime, times the flux that depends on position, E prime, and time. So that Notice that that looks just like the fission production term in my energy dependent diffusion equation. I'm just using this multiplier that's telling me about the number of delayed neutrons that are coming out per fission event. And then I also have my loss term, which is minus lambda I Ci of t. Change rate equals gain rate minus loss rate. So now this is rewriting that original diffusion equation, but we've added in that precursor production term. Or sorry, this is my delayed neutron source term. And now we have an extra equation that tells us about the production of those delayed neutron precursors that appear in my delayed neutron source term. And so notice that equation one depends on the flux and it depends on these concentrations. And equation two also depends on the flux and on these concentrations. So the scalar flux is going to depend on the delayed neutron precursor concentrations. And the delayed neutron precursor concentrations are going to depend on the scalar flux. So these are the equations that we just wrote. B and that concentration are the unknowns that we have in both equations. And that means that we have what would be considered a coupled system. If we want to solve these equations, we need to find phi and we need to find those concentrations. So this is kind of like going to be our starting point from which we will try to understand the impact of delayed neutrons on our system. And we can make progress on this. We're going to make some simplifying assumptions to get a better understanding of this problem. And that's what we're going to do next. So to simplify the problem, we're going to assume that we have an infinite and a homogeneous medium. So if I go back to these equations, if it becomes an infinite medium problem, what term in my diffusion equation goes away if we end up with an infinite medium? Right, there's no leakage from an infinite medium. So this term that has the gradients and the divergences, that's my net leakage term. It goes to zero. And if it's a homogeneous problem, that means that everywhere the material composition is the same. So then we can ignore the R arguments on all of our terms. That's the only changes I've made going to this slide. There's no net leakage term, and now there's no R arguments on any of my terms. And this equation is like an energy dependent rate density. So what I'm going to do next is I'm going to integrate the first equation over all neutron energies E. So I'm just integrating everything in that equation term by term from dE going from 0 to infinity. And those integrals kind of just go in front of everything. Um, on the on the rate of change term, what I've done is I've just pulled the dt operator out front and I put the integral operator back in. Um, that's because the energy integral doesn't affect my time derivative, so it doesn't matter the order in which I do those things. So I'm just pulling the dt term out, and then I'm integrating over energies, and my speed is going to be like kind of related to like my kinetic energy. So my speed does depend on energy, and that means my speed needs to go inside of this energy integral. And then every other term I've just thrown an integral from 0 to infinity on top. So within our equations, like notice that chi sub p is the prompt fission spectrum. We've got a um, we've got a chi sub I, which is like my delayed neutron fission spectrum. And and within my n-scattering term, there's also a probability density function. The probability that's baked into here, my chi sub I and my chi sub p, those are all probability density functions. So when I integrate those probability density functions over all neutron energies, what do I get? You get one, right? All of those integrated over and from 0 to infinity is going to give me a 1. So if I know that, and then I decide to replace that e prime, that e prime variable with just the regular variable e, then my equations are going to look like this. So from there, what I'm going to do is I'm going to notice that I have this sigma total times the flux term on the left side, and I just now have a sigma scatter times the flux on the right side. So if I subtract the scattering term on both sides, then it cancels on the right, and then on the left, I'm going to have a sigma total term minus a sigma scatter term. And what do I get if I do sigma total minus sigma scatter? Sigma absorption, perfect. That becomes sigma A. So that term is going to go away, and then this term is basically just going to become a sigma A term, right? So that's how I get here. And then to kind of move forward, I'm going to recall that my energy dependent neutron density, which is the phi of E and T, just like when before, like with the scalar flux where we said phi equals N times V, we can also do that for an energy dependent energy dependent scalar flux. It's just that I end up with a neutron density that's energy and time dependent times a speed that also is energy dependent. So this N of E and T, that's just my energy dependent neutron density. Um, and the reason I want to do that is to kind of write this equation in terms of the neutron density instead of in terms of the scalar flux. So I can rearrange by dividing both sides by the speed to say that phi of E and T divided by V of E is just my energy dependent neutron density. So I'm going to substitute this in right here. Inside of this integral, instead of having phi over V, I'm just going to have the energy dependent neutron density. So that term is going to look like d by dt of the integral from 0 to infinity of my N of E and T integrated with respect to energy. And then in these other terms, when I have a scalar flux, I'm just going to replace it with this definition. So this absorption term, I'm going to have integral from 0 to infinity of sigma A of E times N of E and T times V of E integrated with respect to energy. My extraneous source term doesn't change. And I'm going to make that same change. I'm going to substitute in this definition into my flux here. So then that fission integral is going to look like 0 to infinity of nu fp of E times sigma f of E times V of E times N of E and T integrated with respect to energy. That's all I've done to get here is I've just made this substitution into my equations. Now my equations, instead of being expressed in terms of the scalar flux or the energy dependent scalar flux, are expressed in terms of the energy dependent neutron density. And we're getting somewhere with this. We can start to hopefully recognize some prior definitions in some of these integrals to continue simplifying our problem. So like if we kind of go term by term, that first integral, that first d by dt term has this integral where this is the energy dependent scalar flux, and we're integrating that energy dependent scalar flux over all neutron energies. So if I take this energy dependent flux and I integrate it over all energies, what is that going to give me by definition? Um, so maybe thinking about the units is helpful because inside of here, this energy dependent flux has units of neutrons per unit volume and per unit energy. And then I'm integrating it out over all energies. So that means that the energy units are going to be gone. Instead of telling me about neutrons per unit volume and per unit energy, it's going to tell me about neutrons per unit volume that have all different energies. And by definition, that's just the neutron density. So it's just that just recovers my N of T, which is the neutron density that we were thinking of when we had one group diffusion theory. So now it has units of neutrons per unit volume. The density is just per unit volume now. Similar thing with this energy dependent source rate. This is like neutrons per unit volume, per unit time, per unit energy. But if I integrate it out over all energies, then it's just going to be telling me about my total source term. So this thing is going to have units of neutrons per unit volume per unit time. And then with this absorption integral, we're going to write it as itself, and then we're going to try to multiply top and bottom by something to make this look like an average. So if I multiply top and bottom by the integral from 0 to infinity of my energy dependent neutron density, I'm going to do that on the top and on the bottom. I've just taken the right-hand side and I've multiplied top and bottom by the same thing. So mathematically, I haven't changed anything. But then I can kind of look at these as I can kind of look at the original term and when I've put in the denominator, and I can realize that, let me do a different color. If I kind of pick out that term, I've got a cross section times a speed times that neutron density integrated over all energies, and then I'm dividing by just the neutron density integrated over all energies. So if I look at those two together, that kind of looks like I'm doing a weighted average of the absorption cross section times the speed, where it's weighted to the energy dependent neutron density. So that term right there and like the blue dashed line, by definition, is going to be the average of my speed times my absorption cross section for this reactor. That's what's in the blue. And then that term in the numerator is what's left over, this guy. This term in the numerator, again, I'm just integrating my energy-dependent neutron density over all energies. And when I do that, I just get back my N of T. So that absorption term simplifies to the average V times sigma A times my neutron density. And that's what we're going to think of that the kind of triangle brackets is denoting an average. So that's what this is. The average of my speed times my macroscopic absorption cross section. So this is a quantity that's a speed times a cross section. So if I think about the units, what are my units of speed? Perfect. And then what are the units of my of a cross section? 1/centimeters, right? So notice that those centimeters are going to top and bottom are going to cancel. So the units of this average quantity are going to be just inverse top. So that was the game with the averages that we played on the absorption term. And if we look at the prompt fission production term, we can do a similar game, and that we can take it and we can multiply top and bottom by that same ratio. And we can recognize then that this is going to give me a weighted average of my prompt neutron number of neutrons per prompt fission times sigma f times my speed. So that's going to be, I'm going to write V times nu fp times sigma f. That's what this term ends up telling me about. It's a weighted average of the nu times the sigma f times the v. And so be careful to not get your I try to make my V look like a regular V, and then I make my nu look kind of curly so that I could tell those apart. If it helps, you could also just like put a little hat on top of the V as a vector, just so that you remember that that's a speed. That's where it gets kind of messy though, is that it's really a speed, it's not a velocity. But if you put a V on top of it, or a hat on top of it, if you're having a hard time telling them apart, you might throw that hat on top. And then this integral up top, that's just my neutron density. Integrating the energy dependent neutron density over all energies just gives me the regular neutron density. So that's what this term ends up simplifying to. And so therefore, I can plug those definitions into my original conservation equation, where that first energy integral gives me the total neutron density. I end up with two terms that contain that total density. One of them was my prompt fission term, which had a plus sign. The other one was my absorption term, which had that minus sign. I've got my total source term, my total source rate density. And then I've got my delayed neutron precursor term, which doesn't change, uh, doesn't need to simplify further. So once we get to here, we just need to define some terms to kind of simplify the result. So one thing that we're going to define is the delayed neutron fraction. Delayed neutron fraction. We use a symbol beta for the delayed neutron fraction. And I'm going to put an overbar on top of it because technically it's representing like the effective delayed neutron fraction. And by definition, this is just the fraction of neutrons that are born delayed. So this physically represents the fraction of neutrons that are born delayed. And so by definition, it's going to look like my delayed neutron production term divided by my total neutron production term. So, but I'm going to write it in terms of those average quantities that we have in our equations. So the delayed neutron term is going to look like V times my nu D times my sigma F weighted average. That would be like my delayed neutron production term. And then the total production term is going to be the average of V times nu F times sigma F. And then the other thing that we're going to define is this LP. And this fancy L with a subscript P represents the average time from prompt neutron birth to absorption. Average time from prompt neutron birth to absorption. And that's where that the average V times the absorption cross section had those units of inverse time. If we flip it and do 1 over that, we're going to get something with units of time, and that's exactly what LP is. It's 1 over the average of my speed times my cross section, my absorption cross section. Mhm. Yeah. So yes, because the total, so the nu F is like all of my neutrons that are born, and then the part up top is just the fraction of those that come out delayed. Yeah, we had kind of just smushed all of them together when we were using new F. It was including the prompt and the delayeds together. And now we're kind of saying some of them are born prompt, some of them are born delayed. And yeah, for every nuclide, you actually have values for these things individually. But yeah, if you do the delayed plus the prompt, those would add together to give you the total. And yeah, the delayed neutron fraction is going to be relatively small, which means that like most of our neutrons are born prompt. But some of them are born delayed, and the fact that they're born delayed at various time scales is what really ends up impacting the ability of us to control our reactors. And they help in a positive way in that with delayed neutrons, our reactors actually become more controllable. If everything was always born prompt, things would be a lot harder to control. Um, so in terms of like finishing to rewrite our equations, we just kind of want to give ourselves the ability to say that this average time from prompt neutron birth to absorption, we give it a name, and that LP, you can call it the prompt neutron lifetime. So like if you don't want to remember, if you instead of having like a physical meaning for it, you can kind of just give it that name, and that is also what it physically represents. And so the next thing we want to introduce is a definition of K for this problem. And K, this is an infinite problem, so there's no leakage. So it's just going to look like production over absorption, but I'm going to write it in terms of these average quantities. So it's going to look like the average of V times nu F times sigma F divided by the average of V times sigma A. Kind of looks just like the regular infinite multiplication factor if I were to knock out the v's and get rid of the average. And then if I take this definition and I use the definition of beta, then I can rewrite K to have my prompt neutron term and the delayed neutron fraction. So the way that's going to look is I'm going to have V times nu F prompt times sigma F divided by 1 minus beta times the average of V sigma A. So I'm basically just taking that definition, plugging in the definition of beta, or making use of the definition of beta to rewrite the multiplication factor in terms of the prompt production term and prompt neutron, number of neutrons born prompt, and then 1 minus the delayed neutron fraction. So plugging things in, making use of those definitions, takes that previous equation that we had and gets us here. And then what we're going to do is we're going to divide top and bottom by the average of V sigma A. So when I take that, when I divide top and bottom by that average, then it kind of just knocks that term out on that first part. So if I look at what this big fraction looks like, the first part here is just going to look like 1 minus beta times K, because I've divided the V sigma A term out. Here, I'm dividing that term by itself, so I get a minus 1. And then down here, I've got 1 over the average of V sigma A. And 1 over V sigma A, by definition, is that prompt neutron lifetime. So down here, I'm going to have LP. All I'm going to do next is I'm just going to distribute the terms in the numerator, like multiply K through by 1 and by negative beta. So that's what I've got here. And then I'm going to take this this term, and I'm going to divide top and bottom now by K. So when I divide top and bottom of that term by K, here I get K minus 1 over K. Here I'm dividing by K so that K cancels, and I just have minus beta. And then down here, I'm going to have LP over K. And then the last things we have to define give us these two terms that are kind of looking a little funny in our equation. So K minus 1 over K, by definition, that is what we call rho, which is the reactivity. So the reactivity is K minus 1 over K. And then this guy in the denominator here, the LP over K, we give that a name, and we call that the mean generation time. This is the mean generation time. By definition, it's LP over K. And that's supposed to be a subscript. And as the name suggests, the mean generation time is the expected time for n neutrons to have n children. And the reactivity is just kind of like another way to talk about K. It's kind of like it tells you about if the reactor is critical or subcritical or supercritical, except in this case, if K equals 1, then I have 0 in the top and 1 in the bottom. So K equals 1 means critical, or rho equals 0 means critical. And then if I'm supercritical, it means K is greater than 1. Like if K was 1.1, I would be supercritical. And that would mean I would have 1 plus 1.1 minus 1 over 1.1, which is going to be a positive number. So if rho is positive, that means I'm supercritical. And then if K was less than 1, subcritical, like if it was 0.9, then I would have 0.9 minus 1, which would be negative 0.1 over something. So if K is subcritical, then the reactivity is less than 1. So in that sense, we can kind of redefine our criticality conditions to say if rho equals 0, that means I'm critical. If rho is positive, that means I'm supercritical. And if rho is negative, that means I'm subcritical. Just another way to define or talk about, is my system critical? In this case, it's like a deviation from criticality. Um, so with all of that being said, that gives me the final form of this equation where this right here was my reactivity. I've got minus beta effective, and then I'm dividing by that mean generation time. And then the only other thing we want to define is the delayed neutron fraction for type I delayed neutron precursors. So that's my beta I. That's my fraction of fission neutrons that are type I delayed. And then by definition, that looks like V times nu di times sigma F over the total. So V times nu F times sigma F. And that, oops, sorry. Introducing this definition allows me to rewrite the precursor concentrations in terms of that beta I value. And so now this is what my complicated energy dependent diffusion term has simplified equation has simplified to. And this is what my precursor density term has simplified to. And as a result, instead of having those very complicated equations, I have two equations that are still slightly complicated, but a lot less so than before. These are now coupled first order ODEs, and that means that we have a good chance of solving them, especially because a lot of the terms that appear in these equations can be treated as constants. Um, so these two groups of equations are what we call the point reactor kinetics equations. These are the point reactor kinetics equations. Notice that this is just one equation, whereas my precursor density term, I actually have a bunch of different equations depending on how many delayed neutron precursor types I have. So really, this is one equation, and this is I numbers of equations. Like if I use a 6-group model, then big I is 6, and that means in total I have 7 equations that I have to work with. The point reactor kinetics equations are like one of the most, along with like one group diffusion to understand like how neutrons distribute themselves spatially in a reactor, which is a very useful model. The point reactor kinetics equations are super useful to understand how do these systems evolve with time. So if you're trying to understand time dependence, point reactor kinetics are very useful. The code that I'm using for my thesis is relap, and all of the like neutronics is just based on the point kinetics equations. And you can add lots of complexity into these equations. Like you can account for feedback and other things. But in general, these are what those equations look like. The name is kind of misleading because when we say point reactor, you might think that we're treating the reactor as a point. Um, we're actually doing the opposite in how we derived this. We assume that was an infinite reactor. So it doesn't treat it as a point. Really, what we're assuming, like by assuming infinite, we're assuming that the flux doesn't vary spatially. Or sorry, we're assuming that the flux doesn't vary, the shape of our flux doesn't vary with time. That shape of our flux might increase or decrease because of our population, our neutron population changing, but we're assuming that the shape of that flux doesn't change with time. Um, so for like breaking our scalar flux into a spatial shape function and a time evolution function, we're saying that the shape of that function, the shape of my flux doesn't change with time. It only changes with position. Um, and yeah, a lot of these quantities themselves can end up depending on my neutron density. So a lot of those quantities end up being time dependent. But there's lots of cases where we can treat them as more or less constant. And if they're constant, we can do analytical solutions. We can use those analytical solutions to understand a lot about how neutrons, how reactor behavior changes with time. So that was kind of what I wanted us to get through today was deriving these equations. When we come into class next time, we're gonna start using them to get some better understanding of like if I drop a control rod into my reactor, how is my neutron population going to change with time? Or if I remove a control rod, or if I have temperature effects, how do those changes to my system impact how the system evolves with time? Um, so, with that being said, that was everything I wanted to cover today. Thank y'all for your time. If y'all have any questions, feel free to let me know. Otherwise, I will see you guys.